Okay, good afternoon, everyone. It's nice to see you in the virtual world again. Please do me a favor. If you can hear me okay, please type yes into the chat window. Okay, thank you. All right, sounds like everybody is hearing me okay. All right, welcome, gang. Just a couple business points. You may have seen that you may have seen already the alert that HAC has in fact decided to keep the campuses closed for the remainder of our semester. So that means, for better or worse, we're stuck with online lectures and online testing to get us through till the end of the semester. Your future lab exams and lecture exams, including the final, will in fact be online through the class marker website that you've come to be accustomed with. So I know that's not necessarily a desirable decision for all of us. Personally, I would love to be back in the classroom, but at this time, it's the decision to keep everyone safe. So if you haven't heard, once again, our semester will be completed online because the campuses are going to remain closed through about May 17th or 18th. So, do you have any questions or concerns at this time? Feel free to unmute your microphone or write a question in the chat window. Okay, everyone seems to be silent at this time, and that's fine. If you do have the ability to turn on the video on your computer and show your smiling face, that would be appreciated, because it's not so fun talking to a computer screen. But at any rate, welcome again. I just want to remind you that you will have your lab exam. Everybody in the course will have their lab exam this coming Monday. Okay, this coming Monday, the 30th. You have your lab exam and it will be on the class marker website. Okay, the class marker website that you've become accustomed to. You have all day to take it from 7 a.m. to midnight. So just like you did for your first lecture exam, log in when you have time and complete your lab exam. Okay, the only portion of the lab exam that I was not able to do is the practical part where I actually have you use a microscope. Since we're not going to physically meet at campus, there's no way that I can test you on your microscope skills. So you get a pass on that this semester. Okay, but everything else that I had hinted at in your study guide before break, I will be testing you on your lab exam this Monday. Do you have any questions about what's going to happen on Monday in terms of the lab exam?
Yes, I do have a question. How long is the exam for again?
How long is the example? Or how long is the exam?
Yeah.
You will have 45 minutes.
Okay.
And I'll be honest with you, Terry, this is not a long exam. I really don't think you're going to need 45 minutes.
Okay.
Okay. We've only done 3 activities this semester in lab. If you think about it, we've only had 3 labs. So it's a pretty modest exam, and I don't think you'll need more than 30 minutes to complete it, but I do give you 45 minutes.
Okay. Awesome. Thank you.
All right. Any other questions?
Is the laboratory number 4 going to be tested on the test?
Lab number 4 is the skeletal and muscular systems. Is that what you're asking about?
Yes.
No, that will not be on this lab exam. You can expect that some of that content may show up on your second lab exam at the end of the semester.
Okay, thank
you.
So
there's plenty of time to go ahead and review that activity. Other questions? Okay, gang. Well, welcome back. And let's get started. What I'm going to do today is finish up chapter 9, hopefully in about 30 minutes or so, and then be on to chapter 10. You can expect that this coming Monday, when you have your lab exam, of course, we will also meet for our normal lecture. This coming Monday, I will be giving you your study guide for lecture exam 2, which is now going to occur on April 6th. So we're getting close, to another lecture exam, and you want to keep up, ask questions as they come up, and make sure you please read your emails every 1 or 2 days so you're not missing important information. Okay, let's get started finishing chapter 9. So I'm going to share my screen again and go back to the Word document and continue our note taking. Okay. Please give me a thumbs up in the video if you can see the Word document. Okay, thank you very much. Let's see. Excuse me for a minute while I try to get the chat window up, because I want to be able to see the chat that may or may not be occurring. Okay. I've got a million windows open right now trying to do a million things. Okay, that seems pretty decent. All right, so if you have a question during the lecture time, feel free to type something into the chat window. Feel free to unmute your microphone and ask a question. That's quite okay. So at the end of last class, am I correct that we kind of did a little silly activity where I showed you how to determine what your dominant eye was? Is that right? Okay. All right. I see Shataria shaking her head. That's magnificent. I can see somebody. Okay. All right. So the last topic about vision that I want to talk about is just cover a couple basic terms that we encounter in everyday life when it comes to eye focusing problems like nearsightedness and farsightedness. Okay, so the truth of the matter is I typically cover these kinds of concepts in lab. We do a nice lab where we have you folks measure your visual acuity with a Snellen eye chart and that kind of thing. And unfortunately now we can't do that because we're all stuck in quarantine, so to speak. But okay, so I just want to put a couple quick definitions down about these things. I know many of you have eyeglasses, wear eyeglasses, or wear contacts. And so focusing problems are talked about on page 158 of your textbook, figure 9.8. And I'm not going to cover all of them, but I'm going to cover 3 of them that are very common. Okay, so let's talk about farsightedness. Okay, farsightedness, the fancy sciencey word for farsightedness is hyperopia. Hyperopia. Okay, and what this means is that when you're farsighted, when you have hyperopia, that means you can see distant objects clearly, but close objects, such as right in front of you, are blurry and out of focus. You can't see them properly. In this condition, you can see distant objects closely, but objects near to you are out of focus. Okay, you can see from the picture on page 158, figure 9.8, you see a picture there of farsightedness. Okay, and you can see that because of changes in the shape of the eye, the light rays that are supposed to focus on the back of the retina actually focus behind the retina. It's kind of weird, okay? So let me see here.
Dr. Todd, I do have a suggestion here. Is there okay, awesome. It's fixed.
Can you see that?
Yeah.
Okay. All right, let me know if you can't see that.
I couldn't first, but now it's fixed.
Okay.
All right.
I realized what was happening. Thank you, Terry. Okay, so in this condition, you can see distant objects closely, but nearby objects are out of focus. The reason this occurs is because the eyeball has an unusual shape that causes light to focus behind the retina. Okay. All right. So, maybe you are farsighted, some folks are. The second very common type of vision problem is nearsightedness, right? Nearsightedness is called myopia. Okay. And in this condition, you can see objects close to you very clearly, but distant objects are blurry and out of focus. And the reason for this that you can see in your book is that the light rays coming into the eye, because of the unusual shape of the eye, causes the light rays to literally come to a focal point, come to a common group point in front of the retina. So with farsightedness, the light rays focus behind the retina, and in nearsightedness, the light rays focus in front of the retina. In this situation, light entering the eyeball focuses in front of the retina. Okay. So for you all know your personal history. I started wearing glasses when I was in 5th grade. I was playing baseball, and I was at a baseball game with my dad, and he asked me what the score was on the scoreboard out in the outfield, and I told him that I couldn't make out the numbers. So obviously, he had a suspicion that something wasn't right. I went and had my eyes tested, and sure enough, in 5th grade, I was diagnosed with myopia. The fact that I could see things close by, but I couldn't see things in a distance. So I've been nearsighted most of my life, and now in my years, many years since playing baseball as a little leaguer, I now have to have myopia, I now have to have bifocals because I'm both nearsighted and farsighted at the same time. So you can see how things deteriorate as we get a little bit older. Okay. The third category of eye problem that I want to put into your notes is astigmatism. Okay. Now, for someone that has astigmatism, you have blurry images, and that's because the shape of the eyeball is uneven at different areas of the eyeball. Okay? You can see in your textbook that because of an irregular shaped eye at literally different, you have an irregular shape at different regions of the eyeball, that the light rays coming into your eye focus unevenly on the retina. Okay? So this produces blurry images because different areas of the eye have different shapes. Okay. In this situation, light entering the eyeball focuses at different places in front of, on the surface of the retina, and behind the retina, all at the same time. Okay, let me review my note here. In this situation, light entering the eyeball focuses at different places in front of the retina, on the surface of the retina, and behind the retina, all at the same time. Okay. All right. So perhaps some of you have an astigmatism. I mean, there are actually different kinds of astigmatism, and maybe you have one of those kinds. Okay. So please speak up, ask questions if you have them. The last topic that I want to talk about here is visual acuity. Okay, visual acuity is a measure of how cleanly you can see an object, how well you can focus on objects. Okay, and visual acuity is typically represented as a ratio. I mean, you've heard 20/20 vision, right? So visual acuity is represented as a ratio, like 20/20 vision, okay? Like 20/20 vision. So let's take this ratio and break it apart, okay? So I'm going to ask this question. What does the top number of the ratio mean? What does the top number of the ratio mean? If you have 20/20 vision, or if you have 30/40 vision, or if you have 50/30 vision, it doesn't matter, it's a ratio. What does the top number mean? Anyone?
Does it mean that's the eye, the other eye, the top number is the eye that you see better? I'm just taking a guess here.
Oh, thanks for participating, Terry. No, it does not mean that, okay? So your answer suggests that maybe you thought that maybe the top number was one of your eyes and the bottom number was the other of your two eyes. That's not the case.
Okay.
Carlos?
Is it meaning based out of 100 that, I mean, if it's 20/40, the lower the number, the better it is?
Not necessarily, no. Anybody else?
Can y'all hear me?
Go ahead.
Is it the maximum that you can get, which is 20? So if you have 20/20, it means that your vision is perfect.
Okay, I think I understand what you're saying. Thank you, Alexi. You're right, 20/20 is typically considered perfect vision, but you understand 20/20 is just a ratio. Like in math class, 20/20 is a ratio. So 20/20 could be perfect vision, but you appreciate that 40/40 could be perfect vision. 10/10 could be perfect vision. 50/50 could be perfect vision.
So 30/40 definitely means there's an imbalance somewhere. It's just.
You're right, there is an imbalance. There is an imbalance. Okay, let's put this in your notes. The top number is the distance that you have to stand to clearly see an object. And so my next question you can imagine is, what does the bottom number of the ratio mean? Okay, folks, the bottom number is the distance that an average healthy person would need to stand to see the same object clearly.
I do have a question, but I'll let you finish typing then.
Okay, Terry, go ahead.
So there's one of my mentor on Instagram. He posted something this morning talking about an implant in the eye, changing the eye color. And this says basically placing an implant on top of the natural iris to change the eye color. Does that change the vision at all, or it's just, it just changes the color? And this is not recommended by the way, because he says there's a lot of risk, but people still get it done.
So that was my first question to you, Terry. Why would somebody want to change? Is the whole purpose of the implant procedure to change the eye color?
Well, I can show you here. He's talking about, you can't see. I think so, yeah.
Okay. So in other words, there's a procedure that will cosmetically allow you to change the color of your eyes?
Yeah. Mm-hmm.
Okay. That seems like a very foolish thing for me. It seems like a very foolish thing from my perspective for a person to do. Here's my response to that, Terry. I'm not familiar with that technology, so I can't tell if it changes your vision. My suspicion is that it will not change your vision, but because you're doing something unnatural to the eye, you open up the possibility of infection and inflammation, which is always a bad thing. So
That's what I thought.
that would be my guess. All right, so before we leave this, okay, let's do this. Let's compare two ratios. Okay, so let's have ratio A be 30/40, and ratio B be 40/30. In this scenario, which person, A or B, which person, A or B, has the better vision? Please type your answer into the chat window. Which person, A or B, has the better vision? Okay, I'm still waiting on responses. Okay. All right. It's hard for me to tally these up, but we definitely had, I would say at least 50% of you said A, and probably the other 50% of you said B. So it's interesting to get your group response on this, because the person with better vision is in fact B. Let's think about that. What does B mean? B means that you, the person looking at the thing, can be 40 feet away from the object and see it clearly, as compared to an average healthy person, which has to be 30 feet, so closer to the same object to see it clearly. Does that make sense? Sometimes that's a little intuitive, okay? So put yourself in the position of the person looking at it. Let's say that your distance is the top number. That means if here I am pointing at something and you can't see what the hell I'm pointing to. You see, I need to be in class in front of you. Okay. If you have 40/30 vision, and that means you can see the object from 40 feet away, and the average person has to be 30 feet away to see the object. The average healthy person has to be closer to the same object to see it, and you can be 40 feet away. You can be further away and still see it clearly, which means person B has the better vision than person A. Okay. So let me write down an interpretation of that, and I'll open it up to any questions you might have. Okay. So the interpretation of of 40/30 is that you can see the object clearly from 40 feet away, but the average person has to be closer, 30 feet from the object to see it clearly. All right. So sometimes this is definitely a concept that I've noticed over the years kind of perplexes some students. So I don't want to leave this till you tell me you're comfortable with this. Okay, thank you, Carlos. You said it does make sense. How about the rest of you? Are you feeling comfortable with this? All right. Okay, I'm seeing some yeses here. Does anybody want me to cover this again? I'm seeing someone on, okay. Owen, you're saying yes, you would like me to cover it again? Okay. So when you interpret this ratio like 20/20, remember the top number is always the distance that you have to stand to see the object clearly. And the bottom number is you're comparing yourself to an average healthy person. So if the distance that you can see the object clearly is larger than the distance the average healthy person has to see it, that means you have better vision because you can see the object from a further distance. Okay. Questions, gang, before we leave this? All right. Okay. So I'm going to let that sit with you for a while. Again, this is kind of a topic that we would have had some fun with in lab. We would have actually measured your visual acuity in lab, and right now we just can't do it. Actually, if you're so motivated and if you find a Snellen eye chart on Google and print it out, tape it to a wall or a door, stand 20 feet away from it, and start reading off the letters on the eye chart with a parent in the room or your wife or spouse, you could actually measure your ratio, your visual acuity, if you wanted to do that. Okay, I'll just put that as a little note. Okay, if you want to measure your visual acuity at home, find a Snellen eye chart on Google Images, print it, tape it to a door or wall, stand 20 feet away from it, and start reading the chart. You will need a partner, a boyfriend, girlfriend, husband, wife, child. You will need a partner to help you read the result. So it is something you could do at home. Thank you, Carlos, for your comment there. Okay, gang. So what I'm going to do is shift gear now to the sense of hearing. I'm not going to spend as much time on this because I definitely need to get to chapter 10 today, but let's talk about hearing a little bit. Okay. Normally in class, if I had an abundance of time, I would walk you through the anatomy that you see on page 161, figure 913. But I think with things being what they are right now, what I will do is trace out a small flow chart for you, a flow diagram that shows you how sound enters your ear and goes through the anatomy of the ear right up to the point that that sound is converted into different forms of communication that your brain can interpret. I mean, let's face it, right now, you might see me on your screen, but you know, you're really listening to what I'm saying. So how is it that you can hear my voice and understand what it is I'm saying? All right, so we're going to take a flow chart and trace out the path that sound takes through the ear. Okay. First off, you need to have a source of sound, like your loudmouth instructor, or a radio that's playing music, or a car driving by outside. So a source of sound, right? That sound that's created from the source is going to travel as waves. So you know about sound waves. It's going to travel as waves into the outer surface of your outer ear, which is actually called the pinna. Please try to look at figure 913. Please try to look at figure 913 as we do this. That way you can see what I'm talking about. Okay, so the sound enters the pinna. Okay. From here, the sound is going to enter what is called the external auditory canal. And you can see the phrase external auditory canal right in the middle of that picture on figure 913. From here, the sound is going to bump up against the tympanic membrane, which you know as the eardrum, right? It's going to hit the eardrum, also called the tympanic membrane. You think about timpani drums, like a percussion instrument that people play at an orchestra or a music concert. Okay, that's what we're referring to. The eardrum is a timpani, a tympanic membrane.
And the tympanic membrane can get messed up while using the cotton tees, right?
It can. You can physically damage it, yes. You can also push earwax onto the surface of the eardrum so that the eardrum doesn't vibrate correctly, right? So I'm not sure how much you folks enjoy listening to loud music, but I'm sure some of you have listened to loud music in your life. Some of you have probably been at obnoxiously loud rock concerts in your life. Have you ever been close enough to a loudspeaker that not only could you hear the sound, but you could feel air being pushed out of it? You know what I'm talking about? Have you ever put your hand up against a speaker and felt the air getting pushed out of the driver of the speaker itself?
Yes.
All right. So, okay. So, you know, as the sound waves hit the eardrum, those sound waves literally physically strike the drum and cause the drum to vibrate in response. Okay. All right. So maybe I'll just put a little note here that the eardrum vibrates in response to sound waves striking the surface. Okay? Now, as the eardrum begins to vibrate, you can notice, if you look very carefully at the picture on figure 913, folks, type into the chat window, what tiny little bone is stitched to part of the eardrum? What tiny little bone is stitched to the part of the eardrum? What's it called? All right, Kira, Shataria, oh, okay, we have a difference of opinion here. Okay, take a very close look. It is in fact the malleus, right? The malleus. So the point is that the eardrum is a piece of tissue and it is stitched to a bone called the malleus. So inside your middle ear, you have these three tiny little bones that you probably learned in high school health class called the hammer, the anvil, and the stirrup. The fancy technical words for them are malleus, incus, and stapes. Okay, so as the eardrum vibrates, it physically moves those tiny little bones. The malleus, incus, and stapes physically move. Okay, remember the malleus is connected to the eardrum. All right. So at this point, gang, you appreciate that the information of the sound waves has been converted into mechanical motion of the eardrum and bones attached to the eardrum. Okay, so that's how should we say this? The information of the sound waves is converted into mechanical motion of the eardrum and attached bones. Information of the sound waves is converted into mechanical motion of the eardrum and attached bones. Okay, so, all right. Are you with me, folks? Are you okay right now? Please ask questions if you have them. All right. So next from this point, you have these tiny little bones that are moving because the eardrum was vibrating. And the eardrum was vibrating because sound waves were striking the surface of the eardrum. So these tiny little bones move in concert with each other in an organized way. And you notice, type into the chat window, gang, what structure of the ear is the stapes bone nestled into? What structure of the ear is the stapes bone nestled into? Okay, Abigail, thank you very much. Abigail was the first to respond. It's the oval window. Good job, good job. Okay, so next we go to the oval window. Okay, gang, the oval window is the entrance, it's the opening to your cochlea. Okay, so if you've ever heard of a cochlear implant, that's what I'm starting to talk about. The oval window is the opening to the cochlea. Okay? All right, so at this point, we have this mechanical motion of these bones, and it's pushing up at the entrance to the cochlea, which is the oval window. So gang, go ahead and turn your page in your textbook to figure 914. Figure 914. Okay, inside the cochlea is fluid. There's a liquid there. And that liquid is moved around by the mechanical motion of those tiny little bones. Okay, so how many of you have ever been to Wildwater Kingdom at Dorney Park or any other water park? You know what I'm talking about. Have you ever taken a tour of these parks or seen a television show where they show you the machinery of the wave pool, where there's these giant mechanical pistons that are physically sloshing the water back and forth to create the waves so you folks can go out there and enjoy yourselves? Okay, so those mechanical pistons at the wave pool, that's what those tiny little bones, the malleus, incus, and stapes are doing. Think of the malleus, incus, and stapes as these giant pistons that are sloshing the water inside the cochlea. Okay? Okay, so the motion of the tiny bones agitates the liquid inside the cochlea. Okay? Kind of like pistons at a wave pool used to create waves. Have I lost you folks? Are you okay? All right. Okay. All right. So the tiny little bones are moving like pistons, and they begin to agitate the liquid inside the oval window, which is part of the cochlea. Okay. So next, if you look carefully at figure 914 there, what you're going to see, take a look carefully at the one cartoon ball when it talks about the spiral organ of Chpt. The spiral organ of Chpt. Do you see that? It's highlighted with a cartoon bubble on figure 914 called the spiral organ of Chpt. That's number 7, the spiral organ of Chpt. This is now completely inside the cochlea. Completely inside the cochlea. And there's some complicated things that go on here, but what I want you to see is, folks, do you see, when you look at that picture, do you see the hair cells? Do you see the hair cells? They have a purplish color with little fibers sticking up off of them. Folks, what do you imagine happens to the hair cells when the liquid on top of them is getting sloshed around by the tiny little bones acting like pistons? What are those hair cells going to do? Aren't they going to kind of move back and forth like this? Okay? So it's the motion of the liquid inside the spiral organ of Chpt that mechanically moves these little hair fibers. Okay? Motion of liquid moves the hair cell fibers. And the hair cell fibers, I'm talking about the hair cells of figure 914. You never knew hearing was so complicated, did you? But everything in the body is complicated and we just take it for granted. Okay? Now, folks, you tell me, what kind of structure or cell is connected to the bottom of those hair cells? What kind of cell or structure is connected to the bottom of those hair cells? What color is the structure attached to the bottom of the hair cells? Okay, I see. Oh, okay. Not the basilar membrane. Okay. So the basilar membrane's green. That's not quite it. Okay, look at the hair cell on the left. Look at the leftmost hair cell on that picture. And okay, so I'm looking at the right picture there of the artist's drawing. Look at the leftmost hair cell. What color is that structure that's connected to the bottom of the hair cell? Ah, Riley has it. Riley has it. It's the auditory nerve, and it's colored yellow in your textbook. That's what I'm trying to get you to see. Okay? So the mechanical motion of the hair cells causes the auditory nerve that's attached to the hair cells to depolarize and begin an action potential. Do you see what anatomy I'm talking about? 8. We have number 8, auditory nerve. Okay? The auditory nerve creates an action potential when it is disturbed by the motion of the hair cell fibers. That action potential travels, obviously, to your brain, and you interpret the sound. Okay. So for those folks that get a cochlear implant, typically that is an electronic device that's able to take the, excuse me, that's able to take the mechanical motion of the liquid inside the cochlea and convert it into electrical signals for the person's brain to understand. Pardon me. Gang, do you have any questions at this time? Okay, it looks like many of you are still busy writing, and that's just fine. I'll ask one more time before I move on to some new content. Is there any questions about this flow chart of how sound moves through the ear?
I had a question.
Okay.
My son had tubes put in his ears to, I guess, drain fluid or not. I just wanted to know, like, where would that have been put in at? I'm trying to figure that out.
Right. So, if you look on page 161, okay, 161, you find the eustachian tube there, okay? If you have too much fluid building up in the ear for whatever reason, because there's a bacterial infection or something going in there, what the doctors do is put tubes in to drain the liquid out of the ear so it doesn't go down the eustachian tube. Because if it goes down the eustachian tube, it's likely to stimulate an even worse infection.
Oh, okay,
Felicia?
thank you.
Okay,
Yeah.
sure. All right. I just wanted to be sure that that answered your question.
I have a question. With there's this like this new way of like actually taking like earwax or anything out of your ear with like put your head on the side and use like a flame or a candle with like something like coming out of your ear. Is that a good way to actually clean your ear rather than using Q-tips?
Carlos, when you say there's a good way to do that, or when you say there's a new way to do that, did a doctor show you that, or is that something you've seen on the internet?
I've seen it on the internet, but I mean, I'm not gonna do it. I mean, I just don't know. I just didn't know.
Yeah, I've seen it on a movie too.
Please don't do that. Please don't do that. Okay. I mean, just having a flame does not sound good. Having a flame close to your face. If you really want to know the answer to that, you don't even want to use a Q-tip to remove the earwax. That's not good because you can actually take the earwax. Let's say that my right hand is the eardrum, and you have toothpick, a cotton swab here. You can actually press the earwax up against the eardrum and impact the eardrum. You don't want to do that. If you truly have a lot of earwax in there, you want to get an earwax removal kit from your pharmacy. Okay, so and this is something you can probably get for about $10 or so at the pharmacy, and it will have a chemical in it that literally softens the earwax. Don't quote me on this because I may be wrong, but I think the chemical is carbamide peroxide or something similar. Okay, carbamide peroxide. So what you do is you drop these carbamide peroxides, a liquid, and you put these drops in your ear, and you put a piece of cotton in your ear and let that chemical sit on the earwax for 15 minutes or so. And what happens is that chemical will soften the earwax. And then what you do is you take the cotton swab out of the earwax and you get a bowl of warm water with a squeezy bulb. And you turn your head to the side and you literally put the warm water into your ear. You flush it in there. And because the chemical softened the earwax will naturally just be pushed out of the ear. And it's much safer than using a flame or a jackhammer or whatever else you're looking at on the internet.
There was this product on commercials probably 5 years ago called a wax vac. That was like a little vacuum that you would just put in your ear, but it didn't actually work. I had one.
Please don't do that either. Okay. I understand. And in fact, Kira, I think that I've seen the commercial for that. There have been documented cases of people trying to use some sort of a vacuum device to suction material out, and you can physically damage the eardrum and interior anatomy of your ear with that. Very dangerous thing to do. Don't ever apply a vacuum to your ear. Okay. Other questions?
So when you listen to really loud music, what part of your ear do you damage?
Well, think about it. The louder the music, the more intense the sound waves that are hitting the eardrum, the more violently the eardrum vibrates, the more forcefully the little bones move, the more violently the liquid in the cochlea sloshes around, and the more agitated the nerve cells become. So
So it's everything.
It's everything, but the part of the anatomy that's most sensitive to that kind of stress is the auditory nerve. The auditory nerve, being made of nervous tissue, is extremely delicate. So the more violently you agitate it with extra loud noise, the more likely it is to become permanently damaged.
Okay, thank you.
Okay, as the auditory nerve becomes damaged, that tissue that's damaged, it gets replaced with scar tissue. And scar tissue can't function like healthy tissue, so you actually lose hearing.
Thank you.
Okay. Any other questions, gang?
I just had a question. I had tubes when I was little too, and they made me get these special ear things that were molded to my ear so that no water could get in them. When water gets stuck in your ear, what part is it stuck in?
Well, that's complicated. I mean, you would think that if we look at if you look at the anatomy on page 161, you know, if you just put some water in your ear, it stays in the external auditory canal. But my suspicion is that in your case and other cases that people have, some of the water is seeping behind the eardrum. And in that case, it gets trapped in the middle ear. And if it gets trapped in the middle ear, it's likely to promote the growth of bacteria and other microorganisms and create an infection.
Okay.
I mean, the water itself is not dangerous, but it's the water that allows microorganisms to grow, and that is dangerous. Other questions? Okay. All right, gang. Thanks for all the good questions. We really do need, go ahead.
Sorry, I had one more question. I've seen, or I've heard, and I've seen people that had migraine issues, and then they will have their ears pierced at certain areas. Is that actually effective or not?
Piercing the ears to solve the migraine problem.
Mm-hmm.
Well, I would never say no to that. I mean, there are, when you say pierce the ears, what part of the ear are you talking about? Do you know, Terry?
Oh, sorry, my microphone was off. So sometimes they'll have it on the top part of their ear, and sometimes on the part that stands it alone before the bigger part of the ear.
Okay. Let me say a couple things. Obviously, along the ear, you're running along the outer surface of your skull. There are blood vessels and nerve endings all up in this anatomy here. So it is possible, but you would have to really, really know what you're doing to make an incision of some kind that might relieve pressure in a blood vessel that might be causing part of the migraine headache issue. So I think it's theoretically possible, but you don't want to go down and let the kid on the street operate on you, right? You need a neurosurgeon to do that kind of thing.
Correct. Okay.
Anything else? Okay, gang. Let's move on to chapter 10. Good questions, but we definitely need to keep on moving here today. Chapter 10 is the endocrine system. Okay, so let's make some new notes here. Okay, so let me remind you that the difference between the exocrine system and the endocrine system, the difference between exocrine glands and endocrine glands, okay, we're talking chapter 10, endocrine, is that the endocrine system is made of tissue that releases substances that we normally call hormones into the bloodstream, okay? There's, medical science has identified well over 100 substances that we call hormones at this point. And every year new hormones are discovered through medical research. So it's not like we understand everything that's in our body at this time. Research is still figuring new things out every year. Okay, so let's see here. Now, if you were in anatomy and physiology, I would require you to know about 80 to 100 different hormones as part of your understanding. That I'm not going to do to you in Biology 111, okay? There will be some specific examples of hormones that I will give you notes on, and certainly anything I give you notes on, I will hold you responsible for. But you can see a broad overview of some of the tissues and glands of the endocrine system on page 173, figure 10.2. Okay, so that's, those are some of the things that we will eventually talk about. But it's important to me that more than knowing a whole list of different hormones, I want you to have a basic understanding of how hormones do what they do in your body. And so to that, I have to talk to you a little bit about two different categories of hormones, which are explained to you on page 174. Okay, two categories of hormones exist in the body. All right. Okay, so you can see for yourself on page 174, figure 10.3 talks about lipid-soluble hormones. Figure 10.4 talks about water-soluble hormones. And those are the two categories we need to think about. So, okay, lipid-soluble. Lipid-soluble hormones would include the hormones of things like testosterone, estrogen, progesterone, that are based off steroids. Okay, so lipid-soluble hormones are often called steroid hormones. Examples include the sex hormones, testosterone, estrogen, progesterone. Okay, and the important thing to appreciate is that these hormones, because they're lipid soluble, they are biochemically compatible with the phospholipids of the plasma membrane, which should tell you that lipid-soluble hormones can pass through the plasma membrane. So lipid-soluble hormones are able to pass through the plasma membrane of cells to deliver their instructions to the cell. This would be in contrast to water-soluble hormones. Water-soluble hormones, okay? Water-soluble hormones can actually be individual amino acids or full-length proteins. And as an example here, I'm going to include, I think the best example I can give you right now is going to be insulin. Okay, example includes insulin, and I know you've all heard of insulin, you know, because of its association with diabetes and diabetic patients. Okay. And it's important that you appreciate that these kinds of hormones, including insulin, these water-soluble hormones, they are not chemically compatible with the phospholipids of the plasma membrane, so they cannot enter the cell. They cannot cross the plasma membrane. And it's because of this that these kinds of hormones actually have to rely on sort of a relay race kind of scenario to get their instructions into the cell. Okay. They use a relay system to get their instructions into a cell. By relay, I want you to think about, you know, a relay race, a track and field relay race where you have one runner holding a baton. That runner runs a lap or something and hands the baton off to another second runner. That runner runs and then hands the baton off again. That's what I mean by a relay system. Okay, gang, any questions before I continue? Feel free to drop a question into the chat box if you want. Okay, so, you know, this is all well and nice, but we need to connect these notes to some kind of deeper understanding here. So what I'm going to attempt to do at this time is make a very cartoonish little drawing for you and use insulin as an example of how water-soluble hormones can impact the behavior of a cell. If you thought my drawing was bad on the whiteboard at school, you wait till you see my drawing right now. It's horrendous. But I still have to do it, and so you can chuckle away at it. Before I do that, I want to make you aware of something. Let's see here. Both water-soluble and lipid-soluble hormones can create acute and chronic effects in a target cell. Okay, and so I want to talk to you about what acute and chronic means here. Okay, so let's just think about this for just a moment. If you had chronic back pain, what would that mean? If you had chronic back pain, what would that mean? Have you ever had chronic back pain?
I think of chronic back pain as being something that's constant something that you're used to in your daily life. It's not usually like a sharp pain. It's something that you have to deal with all the time.
Okay, so it's continuous. Good, thank you, Kira. Chronic, the word chronic suggests it's long lasting. Okay, it doesn't go away very rapidly. Whereas the word acute is, if you had acute back pain, if it was truly acute, it would come on, you would experience it, and then it would go away. So acute means it's very short lasting. I guess I should say it that way, short lasting. In other words, it doesn't last for a long time. Okay? All right, any questions, gang? Okay, so I'm going to give you another 20 seconds to finish your note taking here, and then I'm going to switch my screen on the computer. Okay. Lynn, you're holding your head. Do you have a headache? Am I giving you a headache? Okay. All right. Very good. Here we go, gang. I'm going to abuse you with some horrible drawing at this time. Okay. All right. All right. So, Kira, give me a thumbs up if you can see this PowerPoint blank whites. Okay, thank you. All right, gang. So let's do insulin as a case study with insulin. Okay. Let's see here. All right. And so give yourself a lot of space on your page, maybe about a half a page or something like that, and draw yourself a really big cell. Okay. So it may not be obvious, but this is supposed to be a cell. And can anybody, is anybody able to tell me what kind of cells respond to insulin most? There's two categories of cells that respond to insulin most. What are they? I can't see the chat window right now, so you have to unmute your mic and tell me. Okay, we're getting close on our time, so I'm going to push ahead. Gang, the two kinds of cells that respond best to insulin are skeletal muscle cells and liver cells. So this cell could be a liver cell or a skeletal muscle cell. Okay. All right. So over here, so what I want to do is show you how insulin inserts its instructions into this cell so that the cell changes its behavior. So let me set the backstage. Okay, the backstage is that you ate a meal, and after you ate a meal, your blood sugar went up. Because your blood sugar went up, your pancreas released insulin into the bloodstream. And the reason that insulin is released is because the insulin wants to tell the cells to lower the blood sugar. Okay, so that's the backstory for this drawing. So let's say we have some insulin. I'm going to use a little eye in a triangle to represent insulin symbolically. Okay, eye with the triangle is insulin. All right, so what's going to happen here is that insulin is going to float up to the plasma membrane of the liver or skeletal muscle cell. Now, if I was in class, I would spend some time trying to pull this out of you because I think it's important. But we're getting pretty short on our time. Insulin's a water-soluble hormone, so it is not able to cross the plasma membrane. Okay, that's in your notes. I just put it in your notes. Insulin cannot cross the plasma membrane. So that means embedded in the plasma membrane is an insulin receptor, an IR, insulin receptor. Okay? So insulin binds the insulin receptor, IR. Insulin binds the insulin receptor. Okay? In your textbook, we would be looking at figure 10.4. Now, figure 10.4 is talking about epinephrine. That's a different hormone. Okay? I'm talking to you about insulin. What I'm saying is the basic idea here is the same. So you can see from your textbook that when insulin binds the insulin receptor, that causes a series of different molecules. Let me get a different pen color here. A series of different molecules to be produced. Namely, ATP is converted into cyclic AMP. ATP is converted into cyclic AMP. Okay, ATP goes to cyclic AMP. So let's back up. Let's think about what we already know in the course. Here's what we already know in the course. When insulin binds the insulin receptor, you know that the insulin receptor changes shape. When the insulin receptor changes, when the insulin receptor changes shape, that causes an enzyme which is attached to the underbelly of the insulin receptor to activate and manufacture cyclic AMP from ATP. Can anybody, looking at their textbook, tell me the name of the enzyme that is responsible for converting ATP? Well, okay, your book doesn't have the name of the enzyme. So let me ask this question. Can anybody tell me what color the enzyme is in your textbook that converts ATP to cyclic AMP? Anybody?
Green,
Okay, is it a dark green or a light green?
like a pistachio green.
Okay, pistachio. Okay, I'm going to go with light green, but I would agree with you. Okay, what I'm saying is this step here is made possible due to the presence of an enzyme. That enzyme is called cyclic. Okay, that's C-Y-C-L-I-C, cyclic adenylase. So insulin binds the insulin receptor. When the insulin receptor changes shape, the cyclic adenylase changes shape, and the cyclic adenylase takes ATP and makes cyclic AMP out of it. Okay? Now, something else. In the language of what we're talking about at this time, insulin is the first messenger. Insulin is the first messenger. And cyclic AMP is what, gang? It is the second messenger. Here's the deal. Cyclic AMP is the second messenger because cyclic AMP is manufactured in response to insulin binding to the insulin receptor. Okay, so Cyclic AMP is the second messenger because it is made in response. Sorry, my writing's getting bad. It's made in response to insulin binding. Cyclic AMP is the second messenger because it is made in response to insulin binding. Okay, I see that we are in fact at our endpoint here. So I'm going to stop sharing my screen. And I'm going to ask you before we turn this off, do you have any questions with the conversation right now?
Can we have the screen one more time? I was about to take a picture of it, please.
Okay, hold on. There we go.
This will still be recorded again, I get. Well, it's being recorded, but be put on basically on YouTube. The way
It will be. It will be. I will have it ready for you later today, and I'll send you the link.
Okay, awesome.
All right, thank you. Beautiful drawing, by the way.
Oh my goodness. Okay, folks, do you have any questions right now? Our goal, first off, I will be online here again in 15 minutes for anybody that just needs to have some questions answered about anything. Monday, we're going to finish this conversation about insulin and talk about some other hormones. And Monday, what do you have to take?
Lab exam.
Your lab exam. Thank you very much. Okay, folks, if you don't have any questions and you're not sticking around for the virtual office hour, have a nice weekend. For the rest of you, I will be back in 15 minutes. So about 2:05, I'll be back here if you need any help. Okay, gang.
Thank you. See ya.
See you soon.